All right, and welcome back to Geology, and this is Chapter 21 on global climate change. So, this is kind of an overview of the whole system. The climate system includes the atmosphere, the hydrosphere, the water, the geosphere, the rocks, biosphere, the life, and the cryosphere, which is ice and snow. So, the climate system, this is in your book. We have changes in solar inputs, changes in outgoing radiation, changes in atmospheric composition, changes in the amount of ice-covered land, and so on, along with a lot of influence from the oceans. So how is climate change detected? Techniques for analyzing Earth's climate history goes back to looking at seafloor sediments. The numbers and types of organic remains are indicative of past surface temperatures. We can take a look at the oxygen isotope analysis, looking at different flavors of oxygen in microorganisms that reflect the past temperatures in the past millions of years. Other sources of data for studying past climates include the growth of tree rings, drill cores and glacial ice, pollen contained in sediment and coral reefs, and information found in historical documents. So tree rings are certainly useful. The diameter of those and the width of those tells us a lot of that, along with how many there are. Here's some information about the composition of the atmosphere. Air is a mixture of many discrete gases. After water vapor, dust, and other variable components are removed, nitrogen and oxygen make up 99% of the clean, dry air. And carbon dioxide, although present in minute amounts, greatly influences the heating of the atmosphere. So here we see in the atmosphere it's 78% nitrogen, about 21% oxygen, and then carbon dioxide makes up a very small portion there. You see that in the dark orange, but it does have a lot of influence on global climate change and warming up the atmosphere. So there are basically two important variable components of air, are water vapor and aerosols. Water vapor absorbs infrared radiation given off by the Earth, similar to carbon dioxide. And aerosols are tiny solid and liquid particles that are important because they act as surfaces for condensation and are good absorbers and reflectors of light. We can take a look at pressure changes. Pressure is the weight of the air above us. Average sea level pressure is about 14.7 pounds per square inch. In meteorology, they talk about millibars. So it's about 1,000 millibars, which is about 30 inches of mercury. Pressure decreases with altitude. 1/2 of the atmosphere is below 3.5 miles, and 90% of the atmosphere is below 10 miles. So we can take a look here at that about 3.5 miles up is where half the atmosphere lies. And at the top of Mount Everest, we're looking at about 1/3 of atmospheric pressure for us. Well, the atmosphere is divided up into layers based on temperature. So we start off with the troposphere. It's the bottom layer, the layer we live in. Temperature decreases with altitude, called the environmental lapse rate. And this goes about 3.5 degrees Fahrenheit per 1,000 feet on average. The thickness does vary. Average height is about 12 kilometers, and the outer boundary of this is called the tropopause. Going the next layer up, we go to the stratosphere. It's about 12 to 50 kilometers up. Temperature increases at the top of it because of the ozone layer. And the outer boundary is called the stratopause. In the mesosphere above that, it goes 50 to 80 kilometers up. Temperature again starts to decrease because of the lack of ozone. And the outer boundary of this is called the mesopause. Last layer is very thin, is the thermosphere. There's no well-defined upper limit to it. It just gets thinner and thinner. It's a fraction of the atmospheric mass, and gases move at very high speeds here. So here's the temperature gradient for the atmosphere. You can see that it goes colder as you go up the troposphere, and then you get into the stratosphere and it warms up because of the ozone. Get back into the mesosphere, it goes very cold, and then the thermosphere, where the particles are moving very fast, it gets heated up again. Here are some atmospheric basics. The energy from the sun is electromagnetic radiation, energy emitted in the forms of rays or waves. The key difference among electromagnetic waves is their wavelengths. Some basic laws governing radiation include that all objects emit radiant energy. It's called the blackbody effect. And hotter objects radiate more total energy than do colder objects. The hotter the radiating body, the shorter the wavelengths of maximum radiation. And objects that are good absorbers of radiation are good emitters as well. That goes back to the blackbody theory. About 50% of the solar energy that strikes the atmosphere reaches the surface. 30% is reflected back to space, and 20% is absorbed by clouds and the atmospheric gases. So here's that depicted in a diagram, the solar radiation coming in. About half of it reaches the ground, and the other 50% is either lost to space by reflection or scattering or absorbed by clouds. Here's the core of global climate change, is the greenhouse effect. And it says that radiant energy is absorbed, heats up the Earth, and eventually is re-radiated skyward. Radiation is in the form of long waves, infrared radiation. The atmospheric gases, primarily water vapor and carbon dioxide, are more efficient absorbers of long-wave radiation. And this selective absorption, called the greenhouse effect, results in the warming of the atmosphere. And it's very similar to your car getting heated up on a hot day in summer. So there have been several explanations proposed for trying to describe climate change, and that includes plate tectonics, the variations in Earth's orbit, which we talked about last week, volcanic activity, and changes in the sun's output associated with sunspots, which occurs over an 11-year cycle. Humans have been modifying the environment for thousands of years. The ground cover has been altered by fire and overgrazing, and this results in a modification of climatological factors such as reflectivity, evaporation rates, and surface winds. In addition, carbon dioxide and other trace gases to the atmosphere are likely contributors to global climate change. These trace gases include methane, nitrous oxide, and chlorofluorocarbons, or CFCs. So here we see the carbon dioxide concentrations over the last 400,000 years. And you can see that it does go up and down in a variance. But you see how recently in the time of humans, how it has really shot up. This upward trend started with the Industrial Revolution in the 1780s. So here's the information about climate feedback mechanisms. And this says that when any component of the climate system is altered, scientists must consider many possible outcomes. And these possible outcomes are called climate feedback mechanisms. Changes that reinforce the initial change are called positive feedback mechanisms. An example of this would be warmer surface temperatures cause an increase in evaporation, which further increases temperatures as water vapor absorbs more radiation. A negative feedback on the opposite side produces results that are the opposite of the initial change and tend to offset it. An example of this would be the negative effect of increased cloud cover on the amount of solar energy available to heat the atmosphere. Well, let's look at aerosols. Global climate is affected by human activities that contribute to the atmosphere's aerosol content. They produce a cooling effect by reflecting sunlight back to space. The effect on today's climate is determined by the amount emitted over the course of a few weeks. And by contrast, carbon dioxide remains for much longer spans and influences climates for many decades. What are some of the consequences of global warming? Because the climate system is so complex, predicting specific regional changes related to increased levels of carbon dioxide is speculative at best. However, some possible consequences do include altering the distribution of the world's water resources, a probable rise in sea level, greater intensity of tropical cyclones, which we have seen recently, along with a little bit of a sea rise, and changes in the extent of Arctic sea ice and permafrost. Recently, over the winter, the North Pole was actually a water ocean because the Arctic ice there had melted. This diagram's in your book. We can see here that The Arctic sea ice has really started to shrink, and again, the North Pole became a icy, watery ocean over the summer. Now, due to the complexity of the climate system, not all future shifts can be foreseen. Sudden, unexpected changes in climate are possible, and a constant state of change is very likely. That's all. Hope you do good on the final exams, and we'll see you next time.